1, 2, 1, 2.
In the Connected Age. It was hosted this year by Microsoft. It was our 5th year, and it talks all about the convergence of the internet and traditional entertainment. It was a 2-day event, lots of really exciting stuff, and I think some of you were there. And if the rest of you weren't aware of it, shame on us, because we are doing some great stuff, under Keith's leadership. We plan to actually do that conference again next year. It's usually in the May, June timeframe, and we're looking to probably have it hosted by Google on their campus, so stay tuned for that, and it's one of the benefits of membership here. For those of you who are members, one of the things I wanted to ask you, when you can come up to me privately, I don't want to embarrass you in the group, maybe after, kind of what you value in your SMPTE membership, and what do you need out of SMPTE to help you in your careers. Is it networking? Is it more relevant technical information? We need that feedback to help make SMPTE more relevant to you. So please seek me out after the presentation. I'd like to hear your feedback. And I think with that, we have, so Keith was just reelected. So for those of you who don't know, Keith Graham is our section chair for the next year, so congratulations to him. And then we have one other new officer for the section, Mr. Kent Terry, who will be section manager. He's from Dolby up in San Francisco, and we have a few others who aren't here tonight. So this section and what we do here locally is for you. Also, one other thing, if there are topics, feel free to reach out to any of the SMPTE section officers here, and we'd be glad to take your input and make this organization useful for you. So with that, I'll turn it back over to Keith to introduce. I guess you've already done it, but I'll turn it back over to you.
Thank you, Pat. Right, so Mr. Steve Holmes of Tektronix, and many of you may know him. He's been a great educator of all things measurement and so forth for many years. So, Steve, over to you. Thank you.
Thank you very much, Keith. I want to welcome everybody here tonight. One of the things that I love doing with these is I love interaction between you guys. I'm going to be the first to stand up here and tell you I don't have all the answers. A lot of this stuff is changing very quick, and I've got some really, really good resources back at corporate and other places to go to get answers, but they have no problem telling you that I have no idea on something. Also, I do not have the standards memorized. That's why God made PDFs, is so that we can go to some place and get them verbatim. So, love to go through it. So, with this, one of the things about 4K was, I know our first thinking about it was this going to be another 3D, because from a test and measurement standpoint, 3D was a bust. We put a lot of money into it. We did a lot of work on it and lost our shorts on it from that standpoint. But really, 4K we don't think is going to be that at all, because one of the biggest things is this thing right here. If nothing else, the studios are going to keep this alive. They are spending tons on reproducing film prints, and it's getting harder and harder. There's only one post house that I'm aware of down in Hollywood that will touch and actually do film, as far as any of the chemical part of doing film. Now, there's still a lot of people scanning it, but as far as doing anything with it, almost nobody is not doing anything. I know Paramount a year and a half ago quit all film. They have no film on the lot whatsoever. So it's going away really, really quick. So the industry, for the most part, has accepted that 4K emulates the resolution of 35 millimeter film, and 2K emulates the resolution of 16 millimeter film. Over 80%, it's probably closer to 90% of the digital cinemas that are out and about are all 2K. Most people don't realize that almost all the digital cinemas are actually 2K, not 4K. They're just rolling into 4K cinemas right now, and most of them are having to run twin projectors to get enough brightness to do what they want to be able to do. So it gets a little fun setting some of this stuff up. So the market driver for this starts out with the studios. The second market driver is us, the consumers. And probably the third, probably is actually the second, is the manufacturers. Let's face it. The manufacturers are always looking for the next big buzz to build something new. So all of the TV manufacturers always want something new to sell, something new to have as the big new buzzword. The delivery of 4K right now, this is the list that I was able to pull. This is the list of companies. All of these are streaming services at the moment, but this was much bigger than I thought. Now, some of it's very limited content, but some of these guys have got some pretty good libraries, and they're behind them. I know I live down in Southern California, and I'm walking into post houses, and they've got halls filled up with pallets of film cans that they're going back and rescanning because they've got no 4K masters. All they've got is 2K masters. And they're going back and retelesending this stuff and rescanning them. And most of them are TV episodics or old shows, and they're making 4Ks out of them because the Netflix, the Amazons, and alike want more and more content to put up as 4K content. So when we start talking about image size, 720 by 480 is about that size. 1280 by 720 looks about like that. 1920, what people are kind of calling full HD, is about that size. The 2048 is just a little bit wider, same height. And then we jump into the first of the 4K resolutions, what everybody is kind of nicknamed UHD. So 3840 by 2160 and then we've got 4096 by 2160. It's almost like what we did with the 1080 and the 2K. It's actually 4 times 2K. Now, for the most part, the 3840 is the home delivery spec for the most part, and the 4096 is the cinema delivery. Now, Netflix, I know, is taking 4096, but they are actually cropping it to 3840 when they show it. So they are actually reduced scanning it and actually black barring the top and the bottom of it when they actually show it. Yeah. Cropping it. Well, actually, no. They're scaling. They're scaling. Well, yeah. So they're not. They're actually scaling it down. Yeah, and they're putting bars on top, bottom to keep the 4096 in the delivery. So for the most part, when we deal with 4K, because of the infrastructure and everything else that we've got within the industry, we're starting out with 4 independent images in one way or another. And this was because all of the facilities that we had to haul video around were all based around HD. So we bust the existing image into 4 separate images and then deal with those, either in a 1920 by 1080 or a 2K format, and run through that. So we're going to take a single imager and we're going to break it into 4 sub-images, and for the most part, and this is how things started, things have evolved, but when we started this, the only thing we had out there was either HD or 3G pipes to handle this and move it around. So we're going to bust it up into 4 images and create 4 independent streams. And this is still how 90+% of it's still done today. But in doing that, we have to do a process called debayering, where we take the image and we're going to have to add a complete horizontal interval and a complete vertical interval to it, because SDI will not work without the TRS, without the horizontal or the vertical interval. So we have to add data to it just to get it onto the physical pipes that we have. So there's 2 different formats. There is square division, where we actually just make 4 separate images, which is the simplest. And then there's 4-way interleave, or what's known as 2-sample interleave, where we actually take 2 samples, 2 samples, 2 samples, and we make a little block of data and process it. Now, for the most part, 90%, well, actually 100% of post is done as square division. It's the simplest to do, it's the simplest to make, and if you aren't worried about delays, it's the easiest to deal with. 2SI comes up when you're starting to deal with live traffic, sporting events, where you want to minimize delay, because you might want to convert it from one format to another. And you've got all of the data from all 4 links in these 8 pixels. Typically, it's going to be done in 2 rows, but you can serially process this as the data is being created and change the resolution or process the data. On the square division, you have to completely raster it before you actually do anything with it. So you're going to raster it, do something with it, and then move on. So for live events, most of it's going out to SI, but for the majority of the content, it's still square division where it isn't live, and you're worried about delays. Now we get into color. Everybody's heard about wide color and different color imageries. Just because it's 4K doesn't mean it's going to be wide color. You can actually have 4K and it can be 709 HD color. It can be DCI P3 space, or it can be 2020. Now the imagers and the cameras have no problem making 2020. We have a huge problem at the moment displaying 2020 color. We can only get about 80% of the green. Blue's getting really rough to do. And so there's several different techniques that people are trying to get the colors out. Also, when they pick 2020, the points they picked are actually on the edge of the chart. They're monochromatic points. So technically, the only thing that can actually reproduce them properly is a laser. because they are monochromatic points. But that's not going to be around too much, at least for what you and I are going to get a hold of, other than maybe theatrical for quite a while. Yeah. So, just to give you a comparison, here's our D65 white point, here's the 709, and here is a 2020 triangle. So, with 2020, they're trying to catch as much of the horseshoe as we can and still stay with straight lines, that we aren't dealing with something where we're going outside of the horseshoe necessarily and dealing with this stuff. If you look at a 601 vector scope for SD and a 709 vector scope, from a vector scope perspective, there are very, very little differences between those two. Now, if I laid them on top of one another, you'd see very small differences, but the differences are incredibly small as far as what they do. The colors that they reproduce are virtually identical, because if they weren't, we wouldn't be able to use the same monitors without doing a lot of background work behind the monitor in changing the LUTs and changing the data going to the screen. So when they made HD, they made it land on the same color points. Now, the math for YCBCR is completely different to give us more dynamic range and give us more space within the colors that the human eye sees, primarily between green and magenta. But the colors that actually reproduce are virtually the same. So when we talk about 2020 color space and 709, again, overlaid, there's very little difference between a vector scope display of the two. Because you got to remember, the vector scope only shows CB against CR. It knows nothing about RGB. And you can change the math to put those points at almost anywhere you want. So when they made the math for making YCBCR for 2020, they landed the points at virtually the same, almost the same points on the screen. I know when I first saw our 2020 vector scope, I was expecting that, and I think it's like a 38-degree shift for green, and I kept wanting green to move over, and it just went, and it was just how they made the math. And since a vector scope from a center to the outside edge where the dots are is not anything to do with a legality point, it's just where should 100% bars or 75% bars land, we put the boxes at roughly the same points going out. So they look very similar to each other. Then we get into, has anybody heard of ACES? Okay. So ACES is the Academy's color space. It's typically 32 bits or greater, floating point, and gives the colorist lots and lots of latitude to move things around. They made it a little bit different than XYZ in that they didn't have to cover all of this space down here. They only have a little bit of room, blue, and a little bit of room around green that actually goes outside of the horseshoe that are illegal colors that the human eye can't see. So by reducing and changing the bottom angle, they were able to get 90% or so of the data inside of the positive direction of the vectors. So if you look at kind of what the difference was, so in 2020 they wanted to keep everything that you could do from looking at the angles inside the color. So ACES is a computer-based transform that you're going to do all your coloring in for high-end stuff, and then you're going to choose an output. You're going to convert that to 709, convert it to P3, convert it to 2020 on the output, and then the bit structure that you want. So XYZ, which has been around for a long time, was one of the first approaches to get the full color horseshoe, but it used linear flat straight lines. So in doing that, you end up with one being way out here, one being up here for Y, and you can do an XY and plot anywhere in there, but you've got all of this room down here that's technically infrared, all of this room down here that would be ultraviolet, and you've got a lot of data that you can't use. So theoretically, from a pure data perspective, 2020 or 709 has more data to give to the colors than P3 or XYZ does. It can just point to a wider view. Then we get into how big a screen do you need? So from 4K, you got to get pretty big to see what's going on. Anything but the thing, you've got to get to this line here to see everything, but anything below this red line is going to give you more resolution than what you would get with a conventional 1080 monitor. So at 10 feet, anything in the 55, 60 inch range is going to get you an improvement here over, well, 10 feet, it's got to get out here. Grab the right one. You got to get about 70 to 80 inch to have an improvement at a normal 10-foot viewing distance. So it does look really good, but it gives a lot that I'll talk about in a minute to some things we're doing with HD. JC. Well, pixel size would have something to do, but that's going to say what size the screen is for the most part. So, yeah, you get into dot pitch and things like that, but it really doesn't, that from what I've been able to find. So this is looking at many different sources and compiling the average of probably 15 different sources I was able to pull.
You could relabel that chart with pixel size.
Yeah.
And not change anything else, just relabel.
Yeah. Yes.
Yeah, there is another factor that most people didn't consider doing that. That is the actual absolute brightness.
Yes.
In fact, there have been some tests with 4K screens at typical 14-foot lamps or 48 nits that we
Mm-hmm.
cover. Actually, you can see that the modulation transfer function, absolute brightness, you can't actually resolve at the nominal viewing distance 4K resolution. If you go higher in brightness, our contrast sensitivity goes up.
Yeah.
Suddenly, you can see the
Okay.
spatial.
It would make sense. Yeah. So, from a looking at waveform type perspective, looking at this data, do we do anything different than we've done with SD or HD in looking at this? So I've got a waveform up here, got a vector scope, got a waveform up here, and this particular one's a YPRPB view of this particular picture. And if you actually look at it down here, it is actually a 4K, it's a 3840 by 2160 shot. So from what you and I look at from normal work in looking at waveforms, it looks exactly the same. We still are going to have YPRPB or RGB presentations that are going to look virtually identical on a waveform monitor, and we can look at these in YRGB or RGB displays. The difference is the amount of data that we have represented in each one of these individual pieces is a drastic increase. It's 4 times what we were looking at. So that's where the thing changes. Same thing with the vector scope. It's going to look virtually identical. It's all 4 links composited together and displayed together. Now, a lot of monitors may work if you drop a link, a quad display, you can drop a link, and a lot of monitors will still give you the 3 windows. Most test gear and virtually every piece of processing gear that I've ever touched and seen will not, because it's got to raster that, put it together as a composited image in order to do something with it. Same thing with a waveform monitor. It needs to make a waveform that is a composited of all 4 links, and you drop one of the links and it's missing a quarter of its data. It has no idea what to do with that. Same thing with our diamond display in looking at a gamut view and looking where colors are placed, looking at levels and looking at things. It's going to look virtually the same from that perspective. The difference happens to be now I have 4 different links that I am putting together to composite this picture. So one of the things we need to start thinking about now is interlink timing. So the industry has chosen link A as the reference, and we will look at link B relative to link A, link C relative to link A, and link D relative to link A, and look at how many clocks difference there are between those. And I've got a shot here where, oops, we've got something going off, 494 clocks off, delayed. So that happens to be in between link C and A. So link C is coming in late, so it's going to be moved off. So does that mean that when I look at the picture, am I going to have a big gap between the picture? The SMPTE standard says I can have up to 29 clocks. So am I going to start getting black gaps between the individual sections of my picture? Am I going to have that black bar sitting there between C and D because C's coming in late? Reality is, no, you won't. Because we don't put the picture back together based on raw clocks. We put the picture based together still on the TRS or the EAV SAV. The clock difference is going to tell us our buffer management and how far I need to delay all the other links to match the one that's delayed the most, so that I can line the clocks up with each other and still build a picture. Now, with the SMPTE standard, they didn't make a huge buffer management that is needed for test gear to be legal. So 29 clocks is not a lot. Our box, we found out in doing a lot of testing with a lot of early gear that we had to go a long ways out for some people's gear to be able to tell them what they had that was broke. And so we ended up putting a 10-bit word in. So we've got a 1024-bit buffer. So we can go out 1024 clocks and still resolve the picture and put it back together so that we can tell you how far out you are so you can go fix it, so you know why all the gear isn't working that you're trying to feed. So in this case. Also, we can break the signal down to individual pieces. One of the things I've seen is virtually every piece of gear that will generate 4 independent links can be used for SD, it can be used for HD, it can be used for dual link. There's register settings on each one of these outputs that can actually change where black is, change where the absolute levels are for a given setup. And as with a lot of things in electronics, registers sometimes get stuck and don't get reset correctly. And you can get very unique things. If you look at this picture, can you see something kind of odd with it? Now this is a still frame and it's fairly easy to see what's off. You put moving video in this, you just see that the bottom left corner just looks different than all the rest of it. And if you go back and put in a flat gray field and then break the links apart and look at the Y of link A, the Y of link B, the Y of link C, and the Y of link D, it'll show up pretty drastically for you. Then you can actually even change it back to look at individual red, look at individual blue, look at individual green if it's not just a pure Luma issue, and actually see what is hosed up with being able to look at this stuff. The other thing that we found that's kind of unique is the majority of all material going out 4K is not 16 by 9. It's some other theatrical resolution. So you may have 2.0, you may have 235 content. I did some testing on some stuff that was very, very carefully rescanned and did come up with these values. Please note your results may vary. These are some that I did off of some gear that was scanned very precisely, so it should be very, very accurate. But a lot of things people want to know, so is where does the first pixel start? Because you're coming out of vertical in black and you're going into active in black, and you want to know where did you place the matte on both sides of the pictures, and did you center it correctly? And then you also want to look at both left and right to make sure that the picture was centered correctly when it was scanned and you don't have a little bit of film black sitting on the left side. You won't have a change of horizontal or vertical intervals because it's digital, and if they change, your bit rate's off and the thing's broken even worse. But you can have extra black after the TRS or before the TRS at the other end. So, and there's a lot of different things. So this was just kind of a really quick kind of overview of just raw 4K in and of itself. So this was just kind of set the stage for the next piece I want to talk about and going through here. So, you know, the summary of this piece is the cost of film processing makes 4K very attractive for the studios. Having new TVs to sell makes it really attractive for the manufacturers. Having more stuff to stream for the streaming customers, and then for those of us that sit on the edge that buy all the new stuff, gives us something new to play with and brag about to all of our friends. So most of the UHD that's going out to you or I is actually Quad HD and not Quad 3G. It's typically Quad HD going out because it's YCBCR data. The stuff going out to the theatrical, the films, that is 444 content, and that is going out as 3G content. I have seen 4K in 709, I've seen 4K in P3, and I've seen 4K in 2020. One of the issues we have at this moment is SDI doesn't tell you what color spaces is coming down the pipe. You have to know what it is so you set the device up correctly at the other end. And I'll show you some stuff that even makes it even worse when we get into the HDR section, because the waveform monitor can't tell you what it is either. There's nothing in a waveform monitor that's going to tell you what it is. And everything looks just like HD did when we started this whole mess. So that's the nice part, the comfort piece at the bottom here. So if we jump over here for just a real quick second. So looking at the waveform up here, I've got an RGB waveform up here. Yeah, let me help out the screen a little. Run the graticules up a little. So it's going to look very much from a waveform perspective like 709 did, other than in this case, this is 3840 2997. Since it's 3840 2997, it is Quad HD going out. It just happens to be the content I have. But it's going to look very, very much like HD did from all perspectives. Yes? Well, here, I can... Yeah. So there's a little brighter. Pull it up even more. It just starts blowing things out if I go too bright, even worse than what it was. But the same thing with vector scope. I mean, the vectors look the same way that they do in HD. So other than sizes, and then being able to look at, you know, audio looks the same, but then we can look at one of the pieces that I'll talk a little bit about, which is the video payload ID of the individual 4 links going through here, and what the magic decoder ring will tell you about those video payload IDs and what they'll screw up. And the more important piece is the measurement of that, the 39 clock piece. So in this case, link B is delayed from link A by 1 clock. Link C is exactly on link A, and link D is only off by 1 clock. So very, very well put together on the output here. Pardon me? Yeah, but then it screws up. So let me pull up the next piece here. We'll go in here a little bit, and we'll take a little pause for the cause. But this is where things are going to start getting fun, where all the new stuff's happening, and it's a little bit of a wild, wild west out there still in a lot of what's going on. DSLRs have been doing HDR, high dynamic range, for quite some time, but they do it completely different than what you and I have to do for video. They're able to actually take multiple shots at multiple exposures and then composite those back together and make some remarkably good looking videos, or not good videos, but shots out of that. We have to be able to do this live. So we've got to come up with another way to do this. So HDR has two very key parts to it. One is the monitor that's going to display it, and the other happens to be the camera or the acquisition. You've got to be able to get the data. You've got to be able to display the data that you get. So we're not trying to just make things brighter. We're trying to make things brighter but have more data in it so we can resolve that brightness and not just blow it out. I know the first year at CES when HDR first came out, you walked the floor and all you saw was high contrast. There was very little actual HDR going on. Everybody was just blowing it out like nobody's business. So SDR is what they're calling standard dynamic range now. HDR is for the high dynamic range. So we don't want blown out pictures. We want much better looking pictures that have more depth and the data to fill that out to be able to get there. There are several new terms floating around here. HDR, of course, high dynamic range, WCG, wide color gamut, and it actually just refers to anything wider than 709. P3 is wide color. 2020 is considered wide color. SDR, dynamic range. PQ, the perceptual quantizer, which is the 2084 Barton curve. Ultra high definition is the HDR disc format for HEVC, HDR10, Dolby Vision 12-bit HDR, BT 2020 color space, and with the dynamic metadata. HDR10 is what they're doing on the Blu-ray disc. And someone that the folks across the pond are really pushing, HLG, hybrid log gamut, and I'll talk a little bit about that. The UHD Alliance, a new logo to put on top of TVs that doesn't necessarily always 100% agree with some other standards. Then you get into some of the dynamic metadata, max CLL, which is the maximum content light level, max fall, maximum frame average light level. And then we get into a couple of different mastering metadatas, DMCVT, which is now the dynamic metadata for the transfer of this different dynamic metadata that SMPTE is trying to get their hands around and standardize. HFR, high frame rate, and then with most cases, HEVC, which is the new H.265 encoding in order to get this down to a manageable data rate from something that could be incredibly large. Since it's 4 times the amount of data, HEVC, they claim, has twice the efficiency of H.264, which they claim has twice the efficiency of MPEG-2. So we keep getting improvements with data rates. Then this has also brought out a whole list of brand new standards. We know ITU BT 709, which talked about color space, other things about 16:9 aspect ratios, BT 2020, which dealt with what most of us know it for is white color, but it also talked about things about frame rates, progressive scans, and the like. BT 2100, which primarily the biggest thing people are pulling out of it is bit depth, bit values, and someone actually taking files and actually saying, okay, this is the numbers for files. It goes from 0 to 2084 or 0 to whatever as far as bit depths. And then the 2084 OTF, which is the curve, the Barton PQ curve, so that when we have, instead of a gamma applied, we actually have a logarithmic curve applied. It's going to give us a little bit of different data representations when we look at this. Yeah. Not a problem. Curve. Yeah.
Which varies
Yes.
based on absolute light level.
Yes.
So at light levels, it approximates a square law, which is, conveniently what gamma
Yeah.
CRT legacy stuff does. But at higher brightness levels, we're much more sensitive to changes in light, meaning there are more contrast steps for f-stop at higher light levels, and gamma actually isn't sufficient. That's where it moves to sort of a log-based curve, which is approximated by hybrid log gamma, but it's actually neither.
Yeah.
And so that's what 2084 specifies, based on the best color science from the work of Barton.
Mm-hmm.
Actually measured a number of people who derived that human contrast sensitivity function.
Okay. Thank you.
And 2084 has a uniform solution, a formula you can apply, as well as it's adaptable across a number of quantization bit depths, up to 12, even 16, or 10.
Mm-hmm.
Currently what's being used in broadcast. But for cinema, we agreed with the studios that 12 bits make sure that you're below every step on anywhere from 0 to 10,000 nits below the contrast sensitivity
Of the Barton curve.
So step,
Yeah.
In bits would not be visible on
Yeah.
any set of.
You get under the JND.
Yeah. There's a couple other standards that are coming up dealing with metadata, the color transforms, and other pieces here. And then the one from Arib that is the hybrid log gamut that I'll talk about in a little bit. So from what I've seen and come up with, there's 4 basic approaches to doing HDR in here. You can use the 2084 curve with absolutely no metadata applied at all, and that's basically what the UHD Alliance is pushing. And it's much like what we do right now in 709. You've got a fixed curve, you've got fixed data. As long as the fixed data matches the fixed curve and the monitor agrees, things will come out. There is static metadata, which is what HDR10, the Blu-ray, it's going to send the metadata to the monitor. The monitor then can take the input. There are several different versions of dynamic metadata by Dolby, Philips, Technicolor, and Samsung, and several others, but those are the primary ones for changing the metadata, either on a scene-by-scene or actually a given area within a scene and going through. And then hybrid log gamut uses kind of a unique piece where the bottom half resembles very, very closely to the 2.4 gamma, but the top half is more the contrast sensitivity The data I got it from actually did say it was a logarithmic curve. I don't know, I haven't looked what it is, but the bottom half, top half.
Right, bottom is roughly gamma squared.
Yeah,
Inflection point, and then it shifts.
yeah,
Logarithmic.
ish, yeah. So when we talk about HDR now, since we're talking about being able to have high dynamic range and things brighter, when we deal with things, we're going to measure the amount of light, and we're going to measure it in a unit we call a nit. Now, a nit comes from 1 candela per meter squared, and it comes from the Latin word. And basically, it was formerly called candle power, but it's the amount of light that came out of a common tallow candle, a single candle, within a meter squared distance. 709 was set up that 100% white within 709 was referenced to 100 nits. So the 100% point in 709 also equated to 100 nits. So that was what they based that all on. So when we start looking at different light levels in room conditions and where things are going here, so a typical light can be anything from as low as 15 nits to 500 nits. If you have very, very bright lights, it could get up to around 1500 nits or so. You start looking outside, and that's too many zeros for me to even look at and come up with the numbers behind it. But incredibly huge numbers of nits for direct sunlight. Yeah, very close to a Google. Depending on the LCD TV, like I said, 709 was originally set for 100 nits. Most LCDs are coming out in the 200 nit range, but still 709 was still based on 100 nits for what was going on. They can get down to maybe 0.1 nits black, maybe, if they have very good dense. Most computers come up with around 200 nits. Some computers may go up as high as 400 if it's a very bright screen. And then we get down into the shadows. And shadows could be around 1 nit or 0.1 or even much lower, since got to remember what the reference was 1 candle power. So think about the amount of light a candle puts out. Well, shadows that you and I see can get much darker than that. So that's just to kind of give you a big ballpark reference of all this stuff. So the no tone mapping piece of this is very much like Rec 709. Like I said, the monitor has fixed levels. You expect the monitor to look at whatever the grade was. So if you do 1,000 nit grade on your content, your monitor better be able to put out 1,000 nits, because you're not going to tell it anything about what's coming down the pipe. You're going to have to work on the content just like you worked on the content in 709. You're going to have to make sure all the levels and all the scenes look exactly like you want them to prior to doing anything with it. Send that out to the monitor. The static tone mapping is going to send a set of metadata that will allow the monitor to know the color points, know the color transfer curves, and tell it what it was graded in. So if the monitor can only go up to 700 nits, it can turn around and adjust, scale, adjust to take its input, which might be 1,000 nit grade, and get it into its lighting grade, so that it can adjust things and not clip them off or lose data, and give you a much better representation of what the original content was. Then with the dynamic tone mapping, we have the ability on a scene-by-scene basis to send the data so that we can adjust and get the best possible output on a scene-by-scene basis, or even a subsection of the scene. For the most part, it's done scene by scene, but some cases it could be just the sky area that is being affected. But you're going to send the metadata out for each one of the particular images and send that out. So this is a little old. It may not be 100% up to date, but the folks that were doing Dolby Vision, I know LG has jumped in and is now doing Dolby Vision, but HDR10 is Samsung, Sony, and alike. And are they? Because they were on a big hot camp that they said never, never, never for the longest time. Okay. Okay, I'll have to add that too. Like I said, it's an ever-changing thing, and it's hard to keep up with some of this going on. But my question here is, how much of this is going to stay? How much of it's going to fall off? We all remember Betamax, HD DVDs, and what's going to be the final outcome when of whose HDR is going to survive when, where, is yet to be determined, because some of this I'm sure will fall off the maps and be consolidated down as we go. So the electro-optical transfer function is just a means by taking and telling us how to transfer the electrical signal into optical nits and follow that curve. So it gives us the formula for taking the light sensitivity and putting it in bits, and taking the bits and putting them into the screen and being able to code this stuff. Different people are doing different things for backwards compatibility. I'll talk a little bit about that a little bit later, but that's one of the things that hybrid log gamut brought into the picture without doing anything special. It gave some backwards compatibility without doing some other things to it. So we're going to take a quick look here at gamma curves. Do we need to take a little pause for the cause? Why don't we take a 5-minute break and we'll pick this up about 5 minutes. Okay, let's get going here again. So I'm going to talk just a little bit about gamma, where it came about, how it came into existence with what we have today. So was gamma a CRT defect? Because gamma came about when we started dealing with CRTs. And gamma actually came about because of the way we drove CRTs. CRTs can be absolutely perfectly linear, but you would have to current drive the CRT, not do a grid drive. The grid drive is what causes the gamma curve that we currently have. If we would have chose to do a current drive, cathode drive, the CRTs, they are absolutely linear. The problem is tubes are voltage devices, not current devices. So back 40 some years ago or more, it would have been very difficult to come up with that kind of current to be able to drive the thing. Do we need gamma to match the human visual response? Not really, as long as the display matches what is produced. We don't care what it is, as long as it's faithful and reproducing what's going on. We could do it absolutely linear and flat today. Can you adjust gamma? Well, virtually every TV set in the world today that has an automatic room light sensor on it is adjusting gamma on you every time the sun comes up or somebody shuts the door and it changes brightness in the room. So gamma for a CRT is fairly consistent. It's somewhere around about a 2.4 to 2.5. But what about flat panels? They're actually flat. So, but we needed them to be able to reproduce what we're doing in 601 and 709 in SD and HD. So with BT 1886, they came up and said, you will apply a 2.4 gamma so that the colors will come out correct when you apply a signal to them that already has that gamma in it as an inverse. Why not get rid of gamma with the power law? Well, for the most part, in cameras, quite often they do. They will shoot flat. They will shoot raw and get more data, and then come back and convert it on the back side to get a little more room to be able to work with. Now, if we would have done a linear representation of and got rid of gamma from the beginning, to get 100 steps resolution, it would have taken 15 bits in a linear space. And that would have been outrageous amounts, and we would have needed somewhere around about 90 dB in SNR out of MPEG, which was just out of the question to be able to produce on a easy method. By actually having the gamma curve that we did by grid bias driving the tube, actually 7 bits is enough to give us the resolution of 100 individual steps within what we have. So even though it kind of happened sort of by an accident, by how we chose to drive the CRTs, we would have had to have put some form of curve in order to make television actually work and be able to get the dynamics out of it we wanted to get.
It's the same issue back in the old analog days, the 100 IRE. If you didn't have a gamma, well then you'd have a lot of noise
Yes.
down in the OLN.
Yep. That's why it said you need 90 dB of SNR. So yeah. And that was virtually impossible to get.
Especially out of a
And I forget how many,
transmitter.
yeah, well, and you think about how many bits it would take to get,
I mean, back in the old analog,
yes, yeah.
NTSC and all that.
Yeah, where we were doing good to get 60. So, from a light perspective, our eyes are much more sensitive to changes in dark colors. We see changes that happen in darks better than we see changes that happen in high bright areas. And one of the things you'll see is in like MPEG compression, you'll see something that has a very dark piece to it, and you'll see a lot of mosaic and a lot of running in that dark area. That same change is happening up in the high brights, but the eye doesn't see it. Down in the bottom in the darks, we see that small change a little bit better than we do in the higher bright areas. So one of the things that the Barton curve does for us, and this is what we were talking about with the 12 bits staying below, we were able to stay below the Barton threshold of that J and D where we can see that change throughout this whole thing. So by doing that, we're taking the point here, which you could project up through 400 nits, but again, it's still that gamma curve going on through here. So what they did with hybrid log gamut was they said, okay, well, we're going to keep the bottom end of this up to just a little bit over 100 nits, but from that point on, we are going to extend this out in a logarithmic fashion so that we can get where a normal camera would have put anything above this point, would have put that in the knee and rolled it off at a nice gradual curve so it didn't instantly roll, but it would have rolled off in the knee of the camera. We're going to extend that up so that we can show it. Now, the nice thing about that is if you have a set that can display this, you can get all of that detail up in that bright area that would have been rolled off in the knee of the camera. If you don't, you can stop the signal at 100 IRE and you've got all of the data you would have had in standard 709 or 2.4 gamma to start with. So it's just the point in which you pick and how much data you show. Are you able to bend and have all the specular highlights, or are you able just to show the bottom end of that and you've got standard def TV? Now, one of the things the Barton curve did is, besides lowering this point and going out way past 1200, going out to 10,000, is it went to the left and gave us more data down in the blacks to be able to reproduce those better down in the bottom area, and then give us a lot more data to be able to extend the whites way out and be able to go much brighter. And again, with the contrast sensitivity of the human eye tracking it. So again, one of the things I mentioned before, and this is where things get a little weird in SDI world. 4K can use 709, you can use DCI-P3, or it can use Rec 2020. But one of the unique things in it is that it is absolutely linear in SDI, meaning that when I have a digital value of green and I put out 3AC, which is 100% green, it's going to point to 709. That same 3AC will point to P3 if I tell the receiver it's P3. That same 3AC will point to 2020, 100% green. SDI knows nothing about the difference. It's a digital signal. You're going to put out green. You're going to say it's this value. The receiver says, where does that go? So from a transmission perspective, SDI will look at it and not know until you tell it where it is and what it does. We actually took a device. We've got a rainbow pattern that has every color at every amplitude. Gentleman made it in MathCAD. And it's a sweep of all colors, of all levels. And You see it on a vector scope, completely fills the vector scope, really nice, has all saturations. But you put it in and you put up the receiver and you tell the receiver it's 709, which it was, it fills the entire triangle. We took the same exact signal, just told the receiver it was 2020, and that same 709 signal filled the 2020 triangle perfectly, because SDI doesn't know the difference. So it gets a little hard when we're looking at this. Because display devices are having issues displaying green and some other colors, some manufacturers have asked people to use reduced levels in their colors. And unfortunately, they've used a term which I don't like. They used a term called P3 levels in 2020 color. So what people are doing is they put their device that they're rendering this with into P3 space and say, I'll give you P3 colors, P3 levels. Well, you got to remember where they're working at. That means when you change it back, it's still going to move out. I actually asked people, I said, at what level point do you want green? At what digital value? Tell me that, and then we can meet it. They couldn't do it. Because I've been several post houses where they were switching over and saying, well, they say I got to be P3 levels, so I'll switch over to P3 and make sure I'm not exceeding P3, and then I'll switch back to 2020. And it doesn't work. So it's not a good way to go. Then we get into video levels. So in BT 2100, they define from 0 to 1023 for the 10 bits for a file. And in SDI, we have our EAV, SAV, also known as the TRS, that is reserved code space for the start of active video and end of active video that uses the bottom 4 bits and the top 4 bits. So I cannot get to 0 and I cannot get to 1023. The lowest I can get to is 4, and the highest I can get to is 1019. So you're going to take this file, because you wanted to use the full space, that was done in full, that is 0 to 1023, and when you pull it up in SDI, it's going to come out as 4 to 1019. Now, how did they get there? Did they chop off the bottom 4 bits and the top 4 bits? Or did they rescale it to fit that room? It's up to the software and the output device to make that determination of how you get there. I'm working, I haven't had a chance to make it yet, but I actually want to make a file that is 0 to 1023 and is a nice ramp, because you can play the ramp out, and if you see a nice clean ramp, you're all there. But if you see a flat point take off, a flat end, you know they've clipped it. So I'm going to get some, I'll be able to test different devices with that file and see how they're actually doing full levels. I just haven't had a chance to make it yet. So in here, I've given you 4 different percentages of where 1,000 nits would fall, where 2,000 nits would fall, where 4,000 nits would fall in both standard levels and in full levels. Looking at this stuff. So, looking at this stuff from a file perspective, these are the values that come out of 2110. And so from a SDI perspective, we normally have black at hex 40, and we go up to 3AC for peak white. So we've got extra room above and below that for overshoot and undershoot. But once we go to full level, there is no extra room. So from a normal gamma perspective, this would be any gamma error within standard levels. There is no room, so theoretically from a gamma error, a level error, you cannot have it in full levels because there's no place to go, because you're allowed to use 100% of all the room. But if you hit that point, it's just going to flat top on you. It's going to clip. The same thing if you were doing YCBCR, the levels. So, one of the things we were just talking about, yes, sir. Yes.
Take a while for that to roll out in the equipment, but it's coming.
Yes.
They're also just started a new project to pin down more of the details of what zero is and what peak is in ST2086.
Mm-hmm.
And so hopefully a lot of that will also be
Yes.
as well.
Yeah. But as of right now,
Right now, you have no idea.
no idea. Trust me. I'm dealing with the folks down south a lot with this stuff, and it's a big mess. So the other thing with my understanding is with HDR PQ, there's no real agreed upon diffused white point. So like in 709, if you shot 90% reflective, 100% white, you knew exactly where that fell. If I shoot that white board over there at 90% reflective, you can put it where you want to put it, but you need to be careful because you still need to be able to match from point to point to point. So you need to choose pretty much where you're going to put your diffused white point. Since we came out of a 709 world and we're used to looking at those diffused white levels, we actually chose 100 IRE as a mark that we have in our HDR graticules. So you know at least relative to that, where are you? If you want to put it above it, you want to put it wherever you want to put it, but at least you've got a line in the sand where you're going to deal with doing that. And the same thing goes for camera when you're dealing with capturing in log from a camera to save a lot of work on the back end and post to move it where it should be. So what we chose to do is go ahead and give you the zero nits, 2% reflective, 18% reflective point, and the 100% or 100 nits, which is 90% reflective, the old 100 IRE point, and then 1,000 nit, 2,000, 5,000, 10,000 nit grade points on the screen with the code values. And in this case, this is a full file going from 4 to 1019. So we actually chose to put 4 to 1019 since that is actually what it is. It is not 0, it is not 1023, because SDI can't do that. And there was a lot of discussions in the lab of, well, it's 0, it's 1020, no, it's not. It says SDI can't do that. We can't put something on the screen that SDI cannot do, because you're just going to confuse people worse than what this is going to confuse people. So one of the things you're going to see when you look at something in HDR is the blacks are going to be expanded quite a bit, and then your whites are going to be pulled down. So the PQ curve is always referenced to 10,000 nits. Since most monitors out in the world cannot create 10,000 nits, and in most cases I don't want 10,000 nits in my living room, thank you. And we have energy problems and all kinds of other things on the backside. You'll see that in this case, things are pulled at right at 75% or 1,000 nits. So this was a conventional file that was in SMPTE levels with a 1,000 nit grade on it. And you can see the blacks and how stretched out they are. Here's roughly the same thing going up, but looking at it now in a reflectance. So from cinema aspects, they like to know where the 2% black point is. They like to know where the 18% neutral gray is, and the 90% reflective, which was the old white, maximum white. So what we've done is we've added a reflectance screen. And so you can now look at the data from a reflectance standpoint, and you can see that 1,000 nits would be at 900% reflectance, 900 times wider than what old 709 was, or 601 in that point. Then we can switch also to a relative stop display. And this is almost the equivalent of T-stops because it's through the transfer of the lens into the device. Since it's relative, we had to choose where we say 0 is. So since film work is based on 18% gray, for neutral gray, we chose 18% as our 0 point, and how many stops down for the 2% point, the 90% gray point, and then 1,000 nits up here at 5.6 stops above 18%. So at least relative wise, if you needed to know how much to stop something up or stop something down, you've got a relative judge of where you need to move material.
And it has to be relative because you don't know what the ISO of the source material is.
Exactly. You have no idea what the scene lighting was, whether they stopped the camera to get the proper amount of light. Yeah, so it's purely relative in that. Because they may have done some stuff to get, you know, if you want to get very narrow depth of field, you've got to open the camera up, but then now you've got too much light, so now you're going to ND filter the thing. You're going to drop it down 4 stops with an ND filter to pull the light down so that you can't open the camera up to get a much narrower depth of field.
Great if you can get a hold of that metadata, that descriptive metadata, and feed it into the device in some sort of magical way so that you can figure all that out.
Yeah. Maybe in 20 years. This one is another shot back on SMPTE levels, but with a 2,000 nit grade. So my speculars are going anything above 100 nits, going up to 2,000. So this was a grade done at 2,000 nits. So the specular highlights are from 100 to 2,000 nits in this particular piece. And like I said, at where in full levels, where's 4, where's 1019, and where's normal, and where should most things look like they're fallen, except for the things that you want in the speculars. And there's what 709 would look like sitting on a nit screen. You can see it's 709 because where are most of the blacks? Squished right across the bottom. Where's the top of it going? It looks like it's going up to 10,000 nits because that would be the 100% white point within either 709 or 601. So it's pretty easy to see when you get HDR data or someone feeds you SDR data and you think it's HDR data. Since there's nothing in the metadata yet that tells us what's going on, you need to know what it is. So there's got to be a lot of notes come along with the material when it's being worked on at the moment. The neat thing is, looking at this stuff, is it's really hard to get used to nothing above, if it's 1,000 nit grade, the top quarter of the screen is not used. You aren't really losing that much resolution. You're still using well into the 10-bit range to get there, or well into the 12-bit range if it is 12-bit material. 8-bit material, I forget, I figured it out somewhere, but 8-bit stops way down here someplace. And the rest of that is all the extra material. I know this really threw some guys when the sports guys first looked at this, because they were used to setting cameras a given way, and they ran diffused white all the way up to the top of the screen and wondered why their HDR looked like caca. And it's because they tried to set it up like SDR. They had no idea. The other thing it's nice to be able to do is get into a zoom where you can get into just the specular region and be able to look at it. One of the things you need to be careful about is the amount of content you're catching and putting into the speculars. You need to stay below about 20% max. There is not enough power in the monitors to be able to reproduce more than about 20% speculars. Most of the consumer TVs will actually regulate down and make the entire picture mushy and muddy because you're exceeding their power requirements. Most of the TVs that do 1,000 nits or 2,000 nits don't meet most of the power standards for green compliance and stuff because they can't to get the brightness that they want. And Dolby has come out with some stuff, some of their first stuff in HD HDR. And I've seen HD HDR against 4K, just standard 4K, and HD HDR blows 4K out of the water. So there's a huge push right now for HD HDR because it can fit in our existing pipes that we have. And it looks gorgeous. And I've even seen it on a couple of 4Ks that have up converters in them. And most of the up converters look darn good. So they can take HD HDR and in the scaler, and it looks really, really, really nice in doing this. The other thing that we've put on here is the ability to tell you picture-wise what have you placed and where is it in the picture that you've placed into the specular range. It's a different version of false color, but it's done from zebra striping. So we can zebra stripe, we call it bright ups, the material that you've placed so you can see where am I when I'm grading this stuff, how much of this material, what piece do I want to actually be in the specular zone, what do I want to look normal, and what do I want to pull out in looking at this stuff. So it's kind of a neat way to be able to look at this stuff. Let's see which piece I got up here. So if I put the waveform monitor out of SDR and go down and put it into HDR, now I'm on a 2084 10K curve. I got 0, there's my 2.2 point, there's my 20 nit, there's my 100 nit, and there's 1,000, and you can see this particular material is coming right up to 1,000 and staying there. So this would have been 1,000 nit grade of what's going on in the picture. A lot of people have seen this scene. And then I've got the zebra striping turned on so you can see exactly what's in the speculars and what material should be and shouldn't be. And this was actually done incredibly well. So you see occasionally reflections on her face. All of the fire is in the speculars, and that's what you're seeing dancing around when you look at the waveform. And you see that waveform moving so much. It just changed scenes on me too. So you can see looking out into the sky, all of the pieces that were placed at anything above 100 in looking at this stuff. So we can look at the data, like I said, as a nit screen. I can look at it as stops, look at it as reflectance, or as digital hex values on the right, decimal values, code values on the left. Notice it's gone from 64 to 1023, but 940 would be the normal 3AC point. Of course, this is not full. If I put this in full, then black's going to sit above where my 0 line drops, because I'm not going down, I'm stopping my blacks at 64 rather than going down to 4. But tried to make it really simple to walk between different views, that you didn't have to get into any huge menus. And then one other mode, we do have a camera log mode that I'll talk about in just a second, for being able to look at raw content coming in. Everything from a vector scope perspective is going to look pretty much the same, except for we didn't really rescale the vector scope, so a lot of the data is going to look down. So what a lot of people are doing is they're magging their vector scope out so that they can see the data a little bit better, so you gain it out so you can get the data back about where you're used to looking at it. So I can change the color imagery. It's hard to see, but from auto to 709 to 2020, auto really doesn't do anything right now because no data is being sent. But we've got it there, so when it is, we'll be able to put it on auto and follow it. But like most of the standards when they first come out, about 10% of the content follows it. The rest of it's kind of wide open. It's like when dual link started, nobody told you who was link 1 and link 2. You had to figure it out and then force the scope into the proper mode. But we're trying to get there and be able to put the tools in to be able to use it. We can also set a Luma alarm point. Since you're doing 1,000 nit grade, and 1,000 nits about 75%, and you want to give yourself a little bit of room, you could set it, the Luma point, to a value that gave you a little bit of fudge factor above 1,000, but then it will tell you the exact time code frame that it exceeds whatever your grade value is, and it would put it into the log and tell you the time code frame of every frame that went over whatever your grade value that you chose to be. So the next piece I'm going to talk about is one of the things that's happening with encoding and transmission. And again, bringing up, we do have a VPID, what's known as a VPID, the Video Payload ID. There is several reserved places in the VPID, but it does have data in there to be able to tell you different things about the picture rate, sampling, what link is coming at you, and then you'll see several reserved points in here that there is several bits in the reserve point. So at least color space they could very easily include in the VPID, which I think would be a very appropriate place for it, but I don't know where it's going to end up. One of the unique things looking at this stuff is in order to understand what user word 1, 2, 3, or 4 is and what the datas are, you basically need that magic decoder ring because it's all set in binary. 2 bits mean this, these 2 bits mean this 1 bit means this. And you need to be able to decode that backwards. So we do have a poster that we've come up with. We like making all kinds of posters, but one of the thing is the video payload ID. We actually have all the magic decoder parts in the poster for you, or you just turn on the waveform monitor and we will decode the data and tell you exactly what it is. One of the things I'm seeing a lot though is if you look at this one right here, the 4th user data byte is 01 hex. It says link 1. It's not IDing what is channel 1, what is channel 2, what is channel 3. You have to know. And 90% of the gear I hook up to all shows link 1. Because everybody's making 3G and they're just making 3G how they always made 3G, or they're making HD how they always made HD. The one on the left is actually giving you link 1, link 2, link 3, and link 4 data. And as long as it follows the proper link sequence, and if you notice the rest of the words are all identical because the data better be exactly the same format in every single link. It's one of the reasons this screen's very important. It's when you get things that won't come up. You want to make sure you've got a big problem. And here, every single payload ID is completely the same. In this case, this was quad HD, so this is saying it's quad HD. This one was saying it's quad 3G, but they actually measured. So quad 3G with the link identifier, again, would be link 1, link 1, link 1 if it was 0, 1, 0, 1, 0, 1, 0, 1, which would all be valid and still work. So we key on link A and we expect link B, C, and D to be exactly what link A is, or we're not happy, because then we have no idea what it actually is. So, like I said, the things that you need to know, what curve are you going after? Because it's not told to you. If you're doing HDR, is it PQ curve or hybrid log gamut? What white diffuse point are you going to go for? Are you going to pull up a 1K, 2K, 540? Because 540 is one of the standards for the monitors. So 540 and 1000 nits is part of the UHD logo for monitors. And are you doing full levels or narrow levels? Now that's pretty easy generally to tell because you put it on standard and all your blacks are going down below that. Put it on full and you get your data at the bottom. That one you can figure out by looking at the data on the screen. Most of the rest of this, and for the most part, if the data is already there, you can figure out what the grade is by where it's going. If you're in charge of grading it, you need to know where this is supposed to go in that. So the metadata right now doesn't come in until we hit HDMI. Once we put this into H.265, the metadata will join the video, be put into an SEI message within the H.265 and sent along. In a lot of cases, the material in the file, the metadata may be there, but it's in a sidecar file. And there's no way to include that sidecar file in the SDI yet to get it down to us to tell us what's going on. So someone needs to really know what's going on to look at this stuff. So there's a couple of different ways to get some backwards compatibility going on here. You have an HDR 2084 file, either in SDI or in file format. You run it through some magic dynamic range magic, And in this case, they're sending SDR as the base layer, taking the metadata in how to convert that SDR, what is in the specular highlights above that dynamic range, but sending that metadata and encoding just the SDR, sending that down. You extract the metadata, you decode it. If all you want is SDR, you've got that as the base layer. But if you want HDR, then you've got to do the inverse, pull the metadata out, apply the metadata to that, and then you can come up with your HDR output. There is also inverse of that, where you send HDR as the base layer, and you send metadata, how to pull this HDR down to SDR, and you embed that as metadata. So within the data you're getting, now you can extract that metadata, take your HDR. If you want HDR, you take the base layer out, but if you want SDR, you've got to apply that dynamic range metadata to it to get it down to SDR. And then there is a third method where you just send what it is you get, and you get what is coded, either SDR or HDR. But this is the backward compatibility, so there's two camps out there of going through this. The metadata that's sent, this is what we pull out in one of our tools out of the SEI messaging. It will tell you the primaries, it will tell you the white point, it will tell you what the max level was set for, what the max CLL is. I'm not real happy with max CLL in a lot of cases. The max fall, because one of the issues with max CLL is people have had rogue pixels in a file, and it screws max CLL up badly, because a single pixel can cause that to be wrong. So I think there needs to be a little bit of filtering on that. But so there's been some issues with that. And then look at what the max fall is, what the max level on a frame is, and then color primaries, what they are, and then what the characteristics, and is it constant luminance or not. So that's the metadata that is in HDR10, is sent out one time at the beginning of the file to set the receiver up, tell the receiver where to go. And in the dynamic metadata methods can be sent on scene by scene by scene and be localized or go to a given scene. So the last piece to talk real fast about is camera log, because when we acquire the material, we don't do it in a PQ curve, because PQ curve is not the best thing for an image sensor. A log base is better for the image sensor to get more f-stops. So we want to get as many f-stops as we can in the camera. And by getting as many f-stops as we can, it's very close to a PQ curve, but it's more of a power measurement that we got to put over to a contrast measurement. So there's a LUT that will be applied to take that data and convert it into the 2084 for display. But this gives us the difference of, in this case, this one's looking at S log. This one's looking at log C, which is the Aries log. Since Aries came from a film background, they actually came out with a number of logs that actually go back to a stock of ASA footage, because in the early days they were trying to make their digitals walk into the middle of different film stocks and look exactly the same. Today they can pick one and just go, because there's typically very little film, if any, that they're going to be matching it to. But there's a couple of different logs out there. Everybody's kind of got their own slight difference on their logs that match their electronics, match their sensor, thinks they get the best out of their camera for doing this when we look at the stuff. So you can see that it is a lot like PQ in that it is sort of expanded blacks, a little bit compressed whites, and then with a lot of room for specular highlights. So in this case, we've got a standard grayscale chart in the middle here, but we got this little dude down here. It's a little cube that's got a 18% gray, it's got 90% reflective white, it's got 2% black, it's got absolute black, and then it's got a little polished steel ball on the top of it to give us the speculars. And it allows you to shoot that and actually find where all those different grades are in what you're looking at. It's called a spider cube. Small for looking at what we do in film. It was actually made for DSLR work, but it works really good for doing this stuff. And then I've got a chart in here, if anybody wants it, where code values are for different logs for different percentages. And you can see, based on 100% and 64 for black and 100% white, and what the code values would be for the same for different log formats. So looking at where the 18% gray or the 20 nit point would be, where 100 nits would be, and for your grade level that you want to come in, and whatever work you're going to do to it to get it into a PQ curve. So like I said, the spider cube actually has all those points on it. Makes it really handy to be able to calibrate things and find out where things actually are.
So the super black is essentially a 3D.
Yeah, it's the dark black hole that goes back on the thing, where this is 2% black, 18% gray on reflective, 90% white. It's just a little dude though. It needs to be about yay big. So here's looking at it, and again, log gives you, to get those extra stops, gives you an expanded black zone. So the 2% black, the 18%, and then normal 90%, and then everything above that, depending on your lighting, of how much reflective you're going to get off of that. And then taking that and then running that to 709 and putting things back where they would have been, depending on the LUT you choose to do it. Some do it better than others. I have seen a couple places, did some searching, actually found 2 cameras out there that were doing HDR with twin pickups. One was a single camera mount with 2 sensors, and one was a repurposed 3D rig. And they were compositing the output on the back of that. I haven't really seen those used anywhere that people would put their name behind, because we've been able to achieve what we've needed to be able to do with log on the cameras to get about 16 stops of data back from the cameras today. Okay. Okay. Claims and measurement, because you got glass to go through and a lot of processing and everything else. And very few people actually take raw data. They'll take flat data, but very few take raw data, because you got to do a lot with it.
And also raw isn't really raw.
Yeah.
Lars Borg and I did a presentation at the SMPTE conference talking about raw formats.
There's always something applied to it.
Every camera manufacturer does something to it. You don't really get the raw
Sensor data. Yeah. I like log because at least you know what you're getting. You know what can apply to it. And there's several websites out there that'll give you 3D LUTs to convert it to 709, convert it back to PQ, to convert it where you need to go with it. So that now you've got the stop depth, and now you can get it into something that will output on a screen, and the screen can be reproduced. So We get, different amounts depending on who you read and where you go here. One of the things the human eye is really good at is it can scale or slide fairly quickly. So the eye sees natively about 7 stops, but it can locally adapt to about 10 to 14. And local adaptation is what you would normally see, like if you were looking at a baseball game and you were staring at the field and all of a sudden you glanced up at the stands and the stands were perfect. That's local adaptation. The human eye can go beyond that and somewhere see around 24 stops, but that's the type of thing that when you're outside and you walk into a dark building, we can adapt from that bright sun to the inside, but that takes a little bit longer for the eye to come back. The eye will slide and give us around 10 to 14 stops really quick just by looking at something else. The iris will change enough to be able to see that and be able to adapt to that. And so just depending on the type of device, how much data it will gather, high-end cameras, analog mode, and then just looking at it in different views and different ways. I did not put this slide together. Someone else did that I grabbed from our company. But the adaptive range of what the eye can do. So, like I said, most of the published things, at least what people are actually pulling, is about 16 stops real off of a chart and through the lens and through lighting, normal set lighting. If you wanted to get 20 stops, you'd really have to play with the lighting, and you probably wouldn't be able to use the content, I would think, probably by the time you're done. Yeah. But that kind of shows where we're at with this stuff. There's several references in here. These slide decks will be made available to you. I'll get them up to the website, and you'll have PDFs if anybody wants them of what's going on with these decks. But there's a few references to all this fun stuff in here. I hope you got some good information out of this whole thing. It is still a little bit of the wild, wild west out there. We need a lot of this metadata to come with this stuff. Need a lot of this metadata into the SDI, because it isn't, we got 100% and we know where white is and you don't really need to look at it anymore. We can slide that stuff around all over the place. And when you're trying to take this shot plus this shot plus this shot that were shot by different people at different places and pull them together, there's a lot of things that need to be worked on. And without looking at it, you really can't tell what it is you've got. So I hope you enjoyed the presentation, and I thank you very much.
Okay. Well, thank you, Steve. I hope we all learnt a lot. My brain is aching right now. But, it's great. It's going to be the wave of the future, and so we need to know what we're talking about. So, again, thanks very much for coming. If you're not a SMPTE member, do consider joining. It's very easy. Go to SMPTE.org, and there's a button right on the top there that says join, or something like that. How much do they cost? Not much. In fact, if you're able to, get your company to sponsor you as well. Have them sign up as a corporate sponsor, and you'll get some complimentary memberships that come with it. So that's always a good way. But anyway, thanks very much for coming. Stay tuned for the next meetings. We'll try and set something up for later in July, and we got something very interesting we're hoping to plan for September. So stay tuned for that one, and have a safe trip home. Thank you.
The gear's up here. If anybody wants to see it, ask questions, play with it. My card's up here, Quint's card's up here. But please come on up, push buttons.